All right, hello. Welcome to the second week of class. So, today, just a quick reminder of what we covered last time. We covered charges, we covered how forces, how charges cause forces on each other, likes repel, opposites attract. So if you have two positive charges, they'll repel. If you have two negative charges, they'll repel from each other. And they'll experience a force directly opposite the other, whatever charge it is. If you have multiple charges, you have to break it down in parts. So we're basically going to finish up today with those forces. I'm going to finish the problem I started in last class, which involves some vectors. So I'm going to very quickly kind of review how you break vectors into x and y components and add them up. We've covered, so I'll quickly do that. Again, we'll finish up today. Your first quiz for this class is this Friday. We have covered everything we need to cover, and we'll especially have covered everything. We'll do a bit more practice today, but everything we'll have covered such that you will be able to do the quiz with what I've given you. Granted, please practice using the problem set before you do the quiz. So as a reminder, I give you all this content in the with the PowerPoints, but as far as studying is concerned, as far as checking to make certain you're learning what you're supposed to be learning, there are these problem sets found in web courses in the Files tab. Problem set 1, and they have the solutions, and my solutions is just the numerical answer, because I want you to actually go through the problems. So in this case, the first quiz will be on the first section. So here's what it's going to look like. First one, charges and electric forces. We've covered that. Please go through these, practice them, try them, make certain you understand what to do for those, and that you can get the answer that I've given you. If you can do that, you should be good to go for the quiz. If you know why the answer what it is. The reason I don't give worked out solutions is because it's very easy to look at a worked out solution and be like, oh, yep, makes sense, done. That it is, again, it's like looking at a painting and being like, oh yeah, I can see that they painted here and they made a picture. But I know my artistic skills are not nearly good enough, and if I try to do that, it will be horrendous. It'll be awful. So you have to actually try and practice. That's true of every single... I'm going to turn off these lights at the front. Alright, so just a quick review of how we kind of started this problem. So remind you where we were at with it. We had this problem, we're trying to find the force on the top charge here, charge 3, which is a positive charge. And I gave you actual numbers for it, and we were trying to find the final force on this thing using actual numerical values. So to do that, we broke it down. First, we ignored the negative charge and just said, what is the force on charge 3 due to charge 1? And so that's KQ1, Q3 over R13 squared, where Q1 is a charge of charge 1, Q3 is a charge 3, and R13 is the distance between charge 1 and charge 3. Plug that in, Q over R squared, plug in the numbers, and I'll write the final value in the next slide. Same thing for F23, but that force is going to point towards a negative charge because opposites attract. There's the number for it. And then we had to remember that when you have two vectors, so we have a vector pointed up and to the right and a vector pointed down and to the right, we cannot just add those numbers together because they are not parallel or anti-parallel. You can only add vectors that are parallel or anti-parallel. Another way of saying it is you can only add the x components and the y components and the z components. So 3 dimensions total. In our case, we have 2 dimensions. So that gets us to here. The sum of the forces in the x. That x looks bad, but it's the sum of the forces in x is the components from 1, 3 and 2, 3, the x components. Y is the components of 1, 3y and 2, 3y. All right, great. Simple, but then the part that gets a little tricky is in finding these components. So I drew this, and then I drew it on the next slide, and we'll kind of go through this. To do that, let's just look at 1, 3. Here's our 1, 3. The reminder for you all, and I'm going to do this breakdown this one time, and moving forward I'm not going to spend nearly as much time breaking down the vectors, but this is your kind of review and for your check. So if I want to find the x component is kind of like the shadow that this casts on the x-axis. So it'll be that. And then the y component would be kind of like the shadow. Imagine there's like a shadow of it on the y-axis. That's the way I kind of conceptualize the x and y component. And alternatively, this y component I can move if I want to. I can move it wherever. You can move vectors wherever you want, as long as they maintain the same length in the same direction. The vector here on the left is the same here as it is here, as it is here, it doesn't matter where I draw it on the paper, it's still the same value. So with that in mind, I can move it right on over here because that gives us a triangle. We love triangles because triangles let us do math. And now you have to remember from physics 1 or some of your just trigonometry, how do we find this side of it, the y side of it, and the x side of it given these? Now, one thing so how do we find it? We need to know theta, and one of the things you may think of with this problem is, you'd be like, I didn't give you theta. I did not give you it in the problem, but I did tell you this is an equilateral triangle, and this is where, again, you have to get a bit creative, and you have to look at what's given, and maybe try to find some stuff that's maybe not immediately apparent. So we need to find this angle up here, and you're like, well, how do I do that? All right, so this is where one of those trigonometry theorems come in, is that if you have two parallel lines and you draw a line between them, this angle will be the same as this angle. This angle will be the same as this angle. So there you go. Hopefully you've seen that at some point. With that in mind, what's our two parallel lines? Well, we have this parallel line, and then we have this line going between them. So therefore this angle, call this just theta 1, is equal to that theta 1. Okay, so that's how we did that. That's the thought process there. If you're uncomfortable with that, please do some practice on that because there's not really any tricks to that. You just have to remember some of these trigonometry rules, look at your picture and try to figure out the angles I've given, how can I get that? Because it's an equilateral triangle, I then know that an equilateral triangle, so it has a total, theta total, equals 180. For any object whatsoever, well, 360 actually, my bad. 360. For a triangle, though, it's going to be 180. If you have 4 sides, 360. 3 sides, 180. So theta total equals 180. You can just remember that. So theta total is 180 for a triangle. If I have 3 equivalent things, 180 divided by 3 is going to be 60. So there's a lot of steps I'm doing here. And this is really common in all these physics problems. And honestly, this is going to be very important for you in engineering. Because guess what? In engineering, you are going to have to figure out angles. You're going to have to figure out distances. You're not always going to be able to go to the place and take a protractor and figure out the angle there. You may have to extrapolate it based on other things. So these kind of skills are very transferable to the real world, to what you'll be doing, because you may not have all the information all the time and they may still want you to get the answer. So you're going to have to maybe use some of these skills and some of these logics to do that. Okay. So theta 1 equals 160, great, or equals 60. Okay, then we look at this and remember SOHCAHTOA. So again, I'm kind of outlining every single step here because it may have been a little while. Some of you may be very confident in this, some of you may not be. I'm going to outline it this one time and then not do all these steps moving forward. SOHCAHTOA says that sine of theta equals opposite over hypotenuse. Cosine of theta equals adjacent over hypotenuse. Tangent of theta equals opposite over adjacent. All of these are defined with respect to the angle. So if I say opposite, my angle's here, it's the side that's opposite. If I say adjacent, it's the side that's adjacent. Hypotenuse is the longest side. So if we want let's just see which one. If we want the x component, is that the opposite or the adjacent? Well, it's the adjacent. Which of these has adjacent? These two, tangent and cosine. So then we say, what else do we have? Well, we have the hypotenuse. Which of these has adjacent and hypotenuse? This one, cosine. Now again, this is where I'm saying that one of the misconceptions from physics 1 that a lot of people make is that cosine is what we always use for the x component. That is not the case, because imagine if I gave you this angle. Now my adjacent is the y component, and I would instead be using cosine for the y component. So again, these are all just kind of reminders. You've covered all this, you've seen all this. But I want to make certain it makes sense because you're going to be doing this a lot forever. If you're in statics right now, you best believe you need to know how to do this. Statics is just doing this over and over and over and over and over again. So that's one class we're going to see it a lot. Okay, great. So long story short, we need to find the x components. There you go. So the x net is going to be, sum of the fx's is going to be fx times cosine, not fx, f13 times cosine of 60. And then here's the trick, is it plus or minus? I just told you right now it's plus. cosine of 60. So we need to do it for f(2,3). This angle is also 60 degrees. This angle is also 60 degrees, and that's where, again, you have to use some of your trigonometry knowledge. And this is where if this is 30, so if this one's 60, this is 30. If this is 30, this is 30. If this is 30, this is 60. Okay, make certain that makes sense to you. But that's, again, just where all the trigonometry is coming in. The other one here that you can use, the other trigonometry rule, is that, again, this one is going to equal this one. And so we have this one. Oh, sorry. That's not the right rule that I want to be using here. And I have this angle equals this angle. It's a little tricky to see here, but again, review that, make certain this angle makes sense. It's 60 degrees. It is plus because this one is pointed more to the right than to the left. This one is pointed more to the right than the left. We define positive x. We define to the right on the x-axis as positive. We define to the left on the x-axis as negative. Are these pointed more to the right, or are they pointed more to the left? More to the right, they're positive. Great. Sum of the forces in the y is going to be f(1,3) sine of 60. Sine because now I need the opposite side. Opposite hypotenuse angle. There you go. This one's positive because it's pointed more up than down. The next one is negative because it is pointed more down than up. And if we remember from the previous slide, we found that f(1,3) actually equals f(2,3). And magnitude. Magnitude equals the magnitude. Therefore, this is basically the same thing as f(1,3) sine of 60 minus f(1,3). How did I make that? I'll clarify this. Magnitudes. How did I get from f(2,3) to f(1,3)? Well, if f(1,3) equals f(2,3), I can just plug that in. And then they equal 0. So the y component equals 0. This was a lot of work to prove what you already figured out here. Look, there's no y component here. You already did this. But I'm showing you the math because it's another way to understand it. Sometimes conceptually, it's quick to get this. Sometimes you need to go through the math and be reminded of it. And that's fine. Basically, the math is what I consider like the brute force. If you're uncertain conceptually how to do it, do the math, check your results against that. So, great. Y components cancel. And then the x components is just, I can pick either one. Well, I'll plug it in at this point. So it's 9e to the 9, 3 times 3 divided by 2 squared. Since these are equivalent, I'll write out more steps. Okay, so I took, if f(2,3) equals f(1,3), and I'm adding two like terms, it's just twice as much. So that's the step I did there. And this is going to equal 2 times 9e to the 9 times 3 squared. I'll even put both the 3's there just to make it easier to follow. Divided by 2 squared. Times cosine of 60. And that gives you a number. Whatever, I'll plug it into my calculator. It's a good way to check if you know how to use your calculator. You can check my answer, check to make certain I know how to use my calculator. I will tell you, and this is a good thing to mention now, I will make mistakes in this class. Why? Because I'm a human, and that's going to happen. That is why very often I'm going to want you to be also doing the work to double check my stuff. I will try to make as few mistakes as possible. But I will tell you, no matter how far you get in your career, you're going to make mistakes, and that's okay. The thing that's not okay is not doing everything you can to prevent that mistake in the first place, or not learning from that and moving forward. So please, it is okay to make mistakes in this class, but please learn from them. In my case, the same thing. Last semester, I taught this class for the first time. I made a bunch of mistakes. Bunch more. You aren't going to have to deal with nearly as many as they did last semester. Because of that, the things are way more polished now, and you get a much finer result, but there still will probably be some stuff that may be off here and there. This is natural. I just don't want you all to feel like if you make a mistake that you feel like a failure and you can't learn and you're awful. No. At every single step in the process, all of your professors, no matter how old someone gets, no matter how wise, how learned you think they are, they will make mistakes. They are human. That is normal. Okay? So in the same way, if you think you see a mistake in this, please let me know. because I would much rather correct my mistake and give you all the right answer than sit up here and always be right and you all be getting the wrong information. So please, if there's something you ever think looks off, wrong, let me know. It could even if I am right, it can be a good discussion because maybe there's something that's confusing then that I haven't clarified well enough. So, that's my little soapbox. All right. So we get 2 times 9 e to the 9, 3 squared over 2 squared times cosine of 60. Make certain your calculators in degrees and versus radians. And you get a crazy answer, 2.025 e to the 10, so times 10 to the 10. And remember, this is force, so it's newtons. Ta-da! That's the answer. Everyone else getting that? Yeah? Yeah, great. Okay, I got 2 nods. That's good enough. All right. I put newtons. That's a big deal. Also, you may be like, this number is ridiculous. And you would be right. This is a ridiculous number. That is a very large number. One of the big reasons for that is we have a lot of charge. 3 coulombs of charge is a lot of charge. Remember, what is the charge of an electron? It is 1.602 times 10 to the minus 19. We went from to the minus 19 to 3. That is 19 orders of magnitude larger. So we're going to get a force that's really big. So if you have large amounts of charge stored up, you're going to get a crazy large force. It makes sense when you think about it that way. Most of your problems, you're not going to get this crazy of an answer. I picked easy numbers to make the math easier for us. But in reality, when we're working with point charges, they're going to be closer to the charge of an electron. Great, I did the math for it. It's good stuff. Now I want you all to check your conceptual understanding, and then I'll give you a chance to check your mathematical understanding as well. So we have 3 charges here. It is asking for the direction of the force on the negative lowercase q here. On the far left, we have a positive big Q. Slightly to the right of that is a negative big Q. And then all the way to the right is that negative little q. Is the direction of the force A up, B down, C left, D right, or E, the force on negative q, is 0. The one thing I'll tell you is that the big Q's are different than little q. Bigger or smaller, doesn't matter, but they're different. Alright, gonna wait 5 more seconds, so 5, 4, 3, 2, 1. Alright, awesome. Okay, so let's go through our problem solving process with point charges. Again, we basically look at it and we say, what are we trying to figure out? We're trying to find the force on charge little negative q. So I'm gonna draw that down here to give myself more space. And then remember the strategy is we want to just consider one other charge at a time. So let's just put our negative big Q here. All right, so one at a time. Then we remember, are they opposites? Are they like charges? They're like charges, so they're going to repel. So this little negative Q is going to repel in the complete opposite direction of that one. All right, great. Now we put our positive charge here, and we're just going to consider that one. And then we do the same thing, opposites, so they're going to attract, and it's going to attract in the exact same direction. Draw an arrow here. One thing you notice here is I drew a slightly smaller arrow. The reason being, this is where you have to remember either the equation or the concept. I mean, they're kind of the same thing. The farther away you get from a charge, the weaker the force it's going to experience. So you have 2 charges. The farther you move them away from each other, the weaker the force. So if we keep the 2 charges, the values of the charge is the same, but we change the distance, you're going to get a weaker force. So this one will be stronger, the one on top, the 2 negative charges will be stronger than the one where they're opposite just because the distance is bigger. And again, it's just important to remember the distance is bigger, but the charge value stayed the same. If I had changed these values, if I had said this one was 2Q and this one was just negative Q, I would have to, one, give you more information in this problem for you to be able to solve it. I'd have to actually give you the distances, and you would actually probably have to plug it into the equations to solve it. But because things are kept constant, it makes it easy, life is easy, and it's going to go ahead and move to the right. Because the net force will be this one plus this one, which is going to give you a little one to the right. Or, I don't know, little, big, it doesn't really. Call this situation 1, situation 2, 1, 2, net. Ta-da. All right, great. Easy peasy. So let me give you all the answer. Again, most of y'all got it right. Fantastic. Just make certain you understand the reasoning behind it. I'm not going to do this one because I kind of just did that one with the triangle. But if you want to do that on your own, please do. Okay. I will read through this problem. I will then have you all think about how you would go ahead and do the problem. I'm going to give you some time to think about how you would do it. If you want to go ahead and start trying to do it, please do. But I want you all to think about how you would do it before I start doing it. Because again, once I start doing it, you're going to be like, oh, that makes sense. But it's a lot more learning that happens when you have to push your brain to actually figure it out yourself. So I want to give you time for that. So, a small plastic sphere charged to negative 10 nanocoulombs. Remind you all that nano is times 10 to the minus 9. So whenever you see nano, any unit, it's times 10 to the minus 9, is held 1 centimeter above a small glass bead at rest on a table. The bead has a mass of 15 milligrams and a charge of plus 10 nanocoulombs. Will the glass bead leap up to the plastic sphere? All right, so again, I'll go ahead and at least draw the picture for you all, because I told you all that's an important thing. There's my table. Here's my plastic sphere. Here's my bead. The plastic sphere is negatively charged. This one is positively charged. Spend some time, talk to your neighbors, think about it. How would you go about solving this problem? What concepts do you need? What equations do you need? Think about it. Talk about it. Write about it. All right, so I'll go ahead and start working through it now. Hopefully you have some idea, or maybe you have no idea, and that's fine, but hopefully you spend some time thinking about it. Okay, so we do our thought process for this. First thing, what are we trying to solve for? We are trying to figure out if the glass bead will leap up to the plastic sphere. And this is where you have to use some thinking skills, because leap up is not a jargony word. I doubt you have heard leap up defined in your Physics 1 or Physics, well, we haven't defined in this class, in your Physics 1 class. So this is where you have to recognize, what does it mean to leap up? What does that mean in a physics context? That means that it is going from rest and it is moving upwards. For it to go from no velocity to some velocity means it must accelerate. For it to accelerate, that means it must experience a net force upward. So that's how we connect some everyday jargon into physics words. So solving for F net. Okay? This is now where you want to bring in, if you're solving for F net, this is where you want to go to your Physics 1, and one of the first things you need to remember is if you're doing Physics 1 and you're trying to find F net, free body diagram. Free body diagram is basically a diagram where you have your object. In our case, our object is the one that we care about moving, which is this bottom one, and we draw all the forces acting on it. So, right now, what are the forces acting on it? Gravity. And we have to then think of our force due to electric. We have charges. They are opposite, so they're going to attract. So there will be a force upward. Now that we have this is insufficient by itself to give us the answer, because we need to know how does Fe compare to Fg. So that's step 1, solving for Fe. Step 2 is Fe greater than Fg. Is the force due to the electric field greater than the force due to the gravitational field? If so, yes, it'll go up. If not, nope, it's just chilling there. It will be slightly less heavy feeling. Heavy. If you put it on a scale, it would give you a slightly less value for its weight. But that's not what we're solving for here. So, now we actually have to do some calculations. On to the next page, where I have more room. I will draw my beautiful picture for reference. So negative charge, positive charge. And now that we know how to go about the problem, we need to look at it right. I'm just going to write down all our notes. So we're going to call this one number 1. We're going to call this one number 2. Because I don't want to write out the word plastic. And I don't want to write out the word bead. So the mass of 1 equals who knows what? I don't know. It doesn't tell you. The charge of 1 equals positive or negative 10 e to the negative 9 coulombs. The mass of 2 equals 15 milligrams. So I'm going to write milligrams, but then I'm going to immediately convert that. So 15 times 10 to the minus 3 grams. But then we actually need that in kilograms because everything's in kilograms. So this is one of the really easy mistakes that I've made many a times, is that we consider base units and we're always like, oh, it's the one without the prefixes. But we have to remember for physics, kilogram for some reason is the base unit. So it's 15 e to the minus 6 kilograms. Okay, so that's just a quick reminder. It's really easy to just go from milligrams to grams, but you have to go all the way to kilograms. Because that's what we use in our equations, because someone decided that at some point. So we just have to follow that rule. And Q2 equals 10 minus 9 coulombs. And it's positive, so I didn't write the negative sign there. Great. There we go. So, draw our free body diagram, force gravity, force electric field. Let's just go ahead and solve for them. Force gravity, hopefully you'll remember, that's m times g. If not, please make certain you remember that, because you will be using it in this course. You will use that in life a lot. If you're mechanical or industrial engineering, if people ask you what the force due to gravity is and you don't know it, that will be a sad day if you can't answer it. So, which one? The top one or the bottom one? Well, it's the bottom one, because that's where I drew my forces. So this should be mass 2, and gravity is always gravity. So, go ahead and plug that in. 15 e to the minus 6 kilograms times 9.8 meters per second squared. That gives you a number. And that number is 1.47 e to the minus 4 newtons. And if we wanted to add on to this, so this was just the scalar. I'll go ahead and put this as scalar. If I wanted to give it as the vector, one way of writing that is 1.47 e to the minus 4 newtons in the negative y hat direction. I'm going to try to be using these notations a bit more commonly because, again, you're going to see these from time to time. If you haven't seen y hat, again, I talked about r hat a little bit before, but the reminder is the hat just means it's a unit vector. Unit meaning it has a value of 1, so this just is basically multiplying this number by 1. But then it is a unit vector which points in the y direction. In this case it's negative, so negative y direction. So that's just a way of writing the negative y direction. Again, maybe you've seen it, maybe you haven't. We'll be using that. All right, great. So that's done. Next thing, force due to electric field is going to be K Q1 Q2 over R squared. So, 1 centimeter. Forgot to put that in my notes. So, distance equals 1 centimeter equals 0.01 meters. So we needed that here, so it reminded me I needed to put that there. So 9 e to the 9 times 10. And I'm just going to put the magnitudes of the charges here, and I'll tell you why. It looks like 101, so I'll try to make them bigger. Over 0.01 squared. Okay, so you may be like, why did I put the magnitudes of the charges here? And it'd probably be more appropriate to put the magnitudes here. That is because the negatives, the only purpose of the positive and negatives in the charges is it tells you the direction of the force. Okay, so if you're going to try to plug in the positive and negatives into this equation, that means you're also going to need to know the direction of R and put all that in there. So when I solve these problems, I prefer just put them both as positive and define the direction as a second step. So do the math, figure out the magnitude of FE. Don't worry about the negatives because the negatives do not affect the magnitude. And then the next step, consider, are the charges positive, are they negative? How does that give me the direction? So I do it in 2 steps, magnitude, then direction. That way I don't have to keep track of all the various negatives and positives here because it doesn't change your answer for the magnitude. So again, I'll show you what that means as we go through this. So 90 to the 9. There we go. I was like, yeah, it's going to be way too big. That's how I realized that was off. So 10 e to the minus 9 squared divided by 0.01 squared equals 9 e to the minus 3 newtons. Right now it's a scalar. We need it to be a vector. So this is that second step. I found the magnitude. Great. Now I need the direction. You can tell here in the picture it's positive. That's the nice thing about the picture. Great. It's upwards. It's positive. So it's going to be, and I'll draw my little vector things there. 9 e to the minus 3. And it's a positive, so I didn't write any things there. Positive y hat. Great. Now I just add these numbers because I know that this one is in the y direction, this is in the y direction. They're parallel, well in this case anti-parallel. So F net equals the sum of forces in the y. They're only in the y, which is why I'm just writing the y1. And you get negative 1 point, and I'll just write it FG. You know what? FG minus, or FE minus FG, because they're opposite directions, so I'm kind of including that in there. No, I'll leave it as plus. And then you can plug in the negatives, and that'll make it more clear based on the notation I've been using. So 9 e to the minus 3 minus 1.47 e to the minus 4. You don't really even need to do the math to figure out that this number is bigger than that one. E to the minus 3 is bigger than e to the minus 4, but, you know, we'll do it. The answer didn't, the final response didn't ask for the final answer, but, you know, can't hurt. You get 8.85 e to the minus 3 newtons, and it's positive in the y hat direction. Great. That's it. That's the problem. This is a number. Now we have to interpret it. This is a positive y value. Therefore, positive y, therefore, these 3 dots mean therefore. Maybe you've seen that, maybe you haven't. Therefore is a big word, so we don't write it. We use 3 dots. It moves upward. And as it's moving upward, it will actually increase the force it experiences because it'll get closer and closer and closer and closer. And so at every single step, you could calculate that if you wanted to. I don't recommend, I mean, if you want to, go for it. But it moves upward, so great, done. That is the answer. So this is a very common problem I can ask you throughout the entirety of this course. We're working with forces due to electric fields. Eventually, we will work with forces due to magnetic fields, and we have forces due to gravitational fields. And there's all sorts of other forces that you can characterize it as friction force and all that other forces. And what I can do with this is I can tell you find the net force, and that is a multi-step problem where you will need to remember how to get the electric force, you'll need to remember how to do vectors, you'll need to remember how to add them all up. So very easy problem for me to ask you many variations of. Make certain you remember how to find the net force on objects. That's a physics 1 idea. All we're doing is bringing a different force into it that you didn't have before. All right. Whew, great. We are done with electric forces. So that is done. Again, now we've covered absolutely everything we're going to do for that. That's what's going to be on the first quiz. I will go ahead and give you all a conceptual problem that I just want you to think about. I'm not gonna have you do this problem in this class. I could, but it would just take more time than I think we have able to do it, to develop the skills. But I want you to be able to conceptually do this. So here's my problem. I give you, instead of a point charge, instead of 2 point charges, 3 point charges, I give you an object which has charge distributed across its entire length. And I say, I have a point charge up here. That's a positive point charge. I said, find the force on that charge. I just want you all to spend some time. How would you do that? These are the kind of questions that physicists, that's what we do. We look at a system, we use the knowledge that we've gained. You all have pretty much everything you need to do to conceptually think about how you would go about solving this problem. So you are now the physicist back in the 18th, 17th century, and you are trying to numerically come up with a way that you would solve this problem. Spend some time, think about it. How would you do it? And I'll be curious what you all come up with. Again, I'm not going to have you actually solve this problem, but just conceptually, how would you do it? How do you think you would go about this, using what we have learned thus far? All right, let's hear some ideas. Who has some ideas of how you would go about solving this? Yep.
Calculate the repelling force because same charges repel each other, but also depending on that point charge, if it actually has a mass, you need to calculate the gravity force.
Okay, so calculate repelling force, both positive charges, and account for gravity. Okay? What are some other ideas people have? Maybe some more detailed ones. Yep.
You find the average charge of the rod, like the average position of the charge of the rod.
Find average charge position. And I assume use that just in the Coulomb's law. Okay? These are all good ideas. It's here. Yep.
Take that like distributed charge and kind of convert it to a single point charge.
Okay, so it sounds very similar. Take the distributed one and that like finding the average. So that's another mark for this one. Basically almost like a center of mass kind of deal. Yep.
Integrate the force over the distance from the sun, well, from the point.
So integrate the force over distance. Since we're using some integrals, we're adding up some stuff. Anyone else? All right. So what's interesting is each of these is correct. You are going to need to find the repelling force, and in the real world, you'll probably need to account for gravity. This second one is a maybe kind of situation, and this is more of an approximation. You may do this second one, and this is kind of an interesting thing. If this charge was super far away, that would be really accurate. If this positive charge was super far away, imagine, basically here's my water bottle. You can tell my water bottle has some height to it. But if you were a mile away from me, and you could somehow see this water bottle, what would it look like? It would look like a dot. And this is a really classic tool we use in physics, which is when you get far enough away from stuff, you can approximate it to something else. For instance, a sphere, if you get far enough away, we usually just approximate that as a point. you have to get pretty far, and then it comes to the question, well, how far do you need to be? And that's just where it takes some practice to really figure out where those bounds are, and it depends on the real world. Engineering, sometimes you're gonna have very tight tolerances, and you cannot make many assumptions because it will destroy whatever you're working on. Sometimes you can make assumptions, and you may need to because you don't have much time, or it's just a small thing that you need to do quickly, and it'll work for the problem. This last one, though, is the one that's going to be the most rigorous, where you integrate the force over the distance. And this is, again, where you actually have everything you need to do this. How to do this is going to take time and practice that we don't have the time for, unfortunately. But basically, what I can model this problem as is an infinite number of point charges. I can model this thing on the bottom as being made up of an infinite lot. I say an infinite amount. I can break it into an infinitesimal amount of them, which means there's an infinite amount of them. And then what I would do is I would find the force from this point charge on this one, and the force of this one on this one, and the force of this one, and so on and so on and so on and so on. And this is where an integral comes in. An integral is what you use when you want to add up the contributions of an infinite number of something. So, again, the reason I want to do this is because these are the skills you're going to need in engineering. You are going to be encountering problems where you do not know the answer, but you will have the skills you need to be able to figure out the answer. You'll have the requisite knowledge, or maybe you'll need to research it. It depends. These are the kind of things you're going to have to do in the real world. Some of them do not have answers that people have already figured out. This one does. Everything in this class we're going to be doing pretty much does. Maybe I'll find some ones that don't have answers. And so this is the skills I want to develop. Okay, real quick, I'm going to preview what we're going to cover next time. I'm going to talk about it. That way it sits in your brain for a bit. You can mull it over because it is a very conceptual thing that is going to maybe be weird. But there's math that goes with it too, so we're going to get to that. So we have talked about the forces that two charges place on each other. What is causing that force? Is it just some magic they just do? And this is again where I showed you all that video of Feynman, and it's one of those, how far do you want to go down the line of why? Are you satisfied with two positive charges generate a force and that's good to go? In physics, we're constantly pushing that boundary of what we know, and so we keep asking why. And so we say, why do they cause a force at a distance? What is mediating that thing? And that is where this person, Faraday, introduced this idea of electric fields. He says, well, charges make an electric field, and it is the electric field which is causing the force in something else. So a positive charge makes an electric field. Now, again, I'm going to talk about this more, but I'll tell you an electric field points everywhere away. For a positive charge, it points away from it at every point. So basically what we can say is, imagine this point here. If I said, what is the direction of the electric field here? I draw the tail of the arrow here, and I draw it pointed away from the positive charge. That then tells us that if I put another charge here, we'll say a positive charge, it will experience that electric field due to the other charge, and that electric field causes the force. This may sound really confusing, but this is basically the exact same thing as gravitational field, the exact same concept. Everything with mass makes a gravitational field. When I put something else with mass in that gravitational field, it experiences the gravity. So for instance, my water bottle experiences the gravitational field of the Earth based on what the gravitational field of the Earth is at this exact location. There's a gravitational field every single point. Depending on where I put this, it experiences a different gravitational field. The farther away I get, the weaker it gets. The closer I get, the stronger it gets. It experiences that gravitational field. That gravitational field times the mass gives you the force. Guess what? The electric field times the charge gives you the force. Very strong parallel. If gravity makes sense to you, this is literally just one step past. It is a lateral movement. You're moving from your understanding of that, just replace gravity with electric, replace mass with charge, same thing. All right, you are good to go. If you have any questions, I'm up here. Please come ask me things. Talk to me. I am happy to do so.
I just wanted to ask, on Friday, what material will you be covering? Because I'm going to end up missing class that day.